Okay, first off, my apologies for those of you doing the Java assignment. The issue of kind of getting your state variables that are arrays initialized is, of course, kind of an issue. And the handout incorrectly said to do it in the zero argument constructor, which doesn't make any sense because the zero constructor doesn't know how many it should do. So what did everybody get the announcement that I sent earlier today? Okay, so did that hopefully clear it up? So by the reset method, you know how many are going to be there. So and then the idea there is that you in the reset method, you kind of blow away anything that was there before, and then you add them back in through each of the init. The init for loop kind of loops through it. So for each of the array state variables, the init method should initialize the element of that array for that. And then the only difference is that in the Q state variable, it's an array list instead of an array, because, or a list or whatever your favorite type of list is. But actually what happened on that was originally for some reason in one of the Java releases, they they made it pretty much impossible to create arrays of collections. I'm not entirely clear why, but they did. And so what that means is if you want a collection of if you want an array of collections, you have to do it as an array, as a list of collections. So conceptually it's the same, but so hopefully that everything else is copacetic as far as the that particular assignment goes. And it was kind of the biggest one I've kind of tortured you with, but and as you know, my kind of unhealthy obsession with Little's formula is kind of at play there. But as you can see, it actually does seem to apply in lots of different settings. So what's kind of remarkable about that result is Little's formula is that it holds for just many different types of situations, not just these. Any situation where you have something that comes into a system, stays there for a while, and then leaves, the relationship between the rate at which they arrive, the time that they spend there, and the time average number that are in that thing, Little's formula appears to hold with the same caveats as before. That is, when the system is empty, it literally holds. And if you run the system for like that for a long time, then it will approximately hold. And what you should have been seeing is that it kicks in pretty quickly for under fairly modest assumptions. So and part of the reason that's important is that what that means is that because there are three pieces to that formula, you have the average number in the system, you have the average arrival rate, and then the average time in the system. Whenever you have three things like that have a relationship, if you know two of them, then you know the third, at least approximately. So that's that's a valuable thing. In other words, what that means is that very first simple server that we did, if you wanted to things like the average time in the system, then you could get it without having to actually do any more work on the model itself. In other words, the basic time varying statistics give you enough information under those conditions to do that. I get now the other announcement is we're we're heading into sort of the middle of the quarter. And as mentioned, the syllabus, there is a midterm exam, and that will be a week from today in class. As for those of you who were in the Java course last time, the same circumstances, so you get like a one-page gouge sheet. For those of you coming in remotely, I'll have to figure out how to do that, but I'll be in contact with you, and we'll figure something out. Okay, and there'll be more information about how that's, how that goes and everything. That's not to be honest, that's not something that I really like to do, but actually, recently, the NPS has this WASC accreditation thing, and one of the things that they look at is how does each course evaluate whether or not the students are actually kind of learning what they're supposed to be learning. And so exams are kind of one way of doing that. So that's what we have to do. So I will, okay. Before I get started, yes.
Sure. Can you give us an idea of the nature of kind of what you expect? A lot of emphasis on the event graph.
Yeah, there'll be more information about that. There's going to be, I'll issue like kind of a sample one. Yeah, there'll be the one thing I can promise that there will be one formulation question where I give like a little word problem and say, write an event graph for this. There'll be one of those, and then a few others that kind of address some of the other things that we talk about. Again, there'll be a sample exam. Yeah. Okay, so now today's fun will be, oops. Believe it or not, at some point we're gonna actually do something a little bit different than these cues. We're actually going to model things that kind of move around and detect each other and maybe shoot at each other. We'll see about getting to that, but that's kind of on the horizon. But first, just a few more tweaks on this, and then there's going to be one. I think I'll kind of the capstone model for this is going to be a very interesting kind of model with cranes unloading container ships and switching between one ship and the other. It's a fun model, I guess, where fun depends on what your definition of fun is. Unfortunately, your instructor's definition of fun may differ from yours, but anyway. So, one of the things I hope that is coming across though is this idea of iterative modeling. In other words, the approach is to start with a model that's as simple as possible that captures some element of what you're doing, and then you look at the assumptions of that model, and also its behavior, because when you can implement it as easily as you can kind of turn an event graph into a running program, whether in Java or in Python. Again, sort of ease depends on your mileage may vary, but again, notice that all of the glitches just have to do with things that don't have anything to do with the translating the event graph itself. I mean, there are always some little technical details that you have to worry about. But you kind of look at the system you're modeling, and you look at your model and you say, well, are there any places where the model falls short in terms of capturing an essential element of the system that affects the kind of questions that we're asking? And the questions that you're asking are hopefully addressed by the metrics, that is the various statistics that you're gathering on this. Just on that, notice that we are right now running the model once and then kind of computing averages from within the replication. And the thing to understand, and we'll address this later in the course, is that is basically one roll of the die, or one flip of the coin. And so taking one replication and drawing any significant conclusions from it is, of course, a state of sin. Because in a stochastic situation, you don't know whether the results that you got were something that reflects the nature of the system, or maybe you got lucky, or maybe you were unlucky. You just don't know. So, in other words, supposing somebody hands you a die and you're going to be kind of using this to play a game, and you want to evaluate whether or not the die is fair or not. And so you roll the die once and it comes up 3. Now, is it fair? Yeah, who the heck knows? What would you have to do to decide whether or not it's a fair die? Roll it a bazillion times, measure each one, and okay, so let's say you roll it like 100 times, or I actually ideally a multiple of 6 times, and then you count how many times each number came up. And of course, they're not going to come up, equally, even if it's a fair die, right? So then what would you do? You've all had statistics, haven't you? You'd apply a statistical test where the null hypothesis is, these are kind of goodness of fit tests. So they kind of work the opposite of what your normal hypotheses are, but it's like, are the numbers that we got within reasonable statistical capabilities, without getting into the details. In other words, you need to run it multiple times. So we've been running our model once. And so what we need to do is if we want any usable results, we need to run it multiple times. We'll talk about that later. But okay, so back to the iterative modeling, we look at our model and we say, our multiple server queue assumes infinite room for the queue. In some situations, that's a reasonable assumption. Like the food court, there's no limit to how many of you can wait online. I mean, it's like you have the whole campus, so it's like not an issue. In many situations, it's a reasonable assumption, even though it's not literally true. In other situations, it's sort of an issue. Man, yesterday I was coming back, in and out. It's like every time I'm going that way on Del Monte. I mean, there are these people who kind of block Del Monte, but still, that's still a fine. I mean, they don't block Del Monte all the way up to NPS. They still, so it's like, there is a finite capacity there. So the infinite capacity assumption is not a good one because there is clearly finite capacity. Okay. So in our first model for today, we kind of observe our servers, and our servers they could be machines, they could be people, they could be robots, they could be computer programs. We don't know what they are, but we notice. So let's just sort of come back to people. So our servers are people, and we notice that some of them are faster than others. Is it reasonable that each person would be better at a particular task than others? What ingredients go into that? You have skill, you have depending on the training, you have a number of different elements would cause one server to be different than the other. Our multiple server queue assumption so far has assumed that they were all the same. So even when we had 2 different types, within each type, they were all the same. And so now we're just going to go to our basic multiple server queue, and then we notice that some of them are more efficient than others. Some of them are more effective, just in terms of their speed. And so our model doesn't do that. So can we capture what that is about? Some of the question, if we had a model that could adjust the speed of a server, for example, depending on, we could ask questions like, what would be the effect of, say, if we could have increased training, say, and say improve them by 10%. So if they were 10% faster, then what would the impact of that be? Or if we could train one of the servers to be 10% faster, then what would the impact of that be? We can ask questions like that if we had a model that could do that. We can't ask that question of our basic model, except in very crude ways. Okay. So looking at our multiple server queue yet again, so we'll say that each server is going to have an efficiency. And then we'll have our customers kind of come in with their processing times, just to kind of do it a little bit differently than we had before. And so when the customers process that, they come in, they have a certain amount of time, which is, what would that be? It might be something like, they have their task requires a certain amount of time to produce. So, like say, if it's a bank, if it's say a simple deposit versus a more complicated transaction, those are going to take different amounts of time. Okay, so now to do that, one of the ways that we introduced additional characteristics of our customer was through entities. So for example, in the Reneg model, we had this Reneg time for each customer that they came in with. And they also came in with their service time. So let's do the same thing for a server. Now each server is going to have an efficiency. And so this is kind of how it would look. So we have our entity superclass, which has all of the different characteristics we had. And then, so now for our server, we're going to add just a double value that's going to be its efficiency. And now for a customer, they're going to have their processing time. This is going to be just a simpler version of what we did with the Reneg model. And so now for our server component, if we just kind of look at our state variables, now we had our first in, first out container of waiting customers, which was initially empty. But now that we have servers as entities, what we're going to do is have another container of available server entities. So if I have 5 servers, I'm going to have 5 server entities, and they're just going to be in this container. But initially, though, we need to have all the servers that we have available there. So our parameter is going to be basically an array of server instances. So that's going to be our one parameter. If you remember, once we took the service times and took them out of the server and gave them to the customer, then all we had were the number of servers. And now instead of the number of servers, what we need is the specific instances of each one. Okay, are you tracking all this? Okay. And then, just because we have entities, we can also do the delays in the queue and the time in the system, as well as our other usual suspects. And so now, in order to collect we've done this already a couple times. The number in the queue is going to be collected with this collection size thing. And now if we want the average number of available servers, we're going to also have a collection size for that. So we have on the implementation side, we have all the mechanism to handle this. So let's look at now how this server component is going to look. Okay, so first of all, and this is kind of how, I mean, if we kind of squint our eyes a little bit, this is similar to how the transfer line implementation is going to go. So first we're going to, in the run method, we're going to clear these arrays, and then we can initialize our scalar arrays. But now, in the init, each init is going to have an index, and that index is going to be the number that we're going to look at is just the length of these, all I'm calling all. These are all the server entities. And so for each time we hit init, the init event, we're going to add the server entity at that index to our container of available servers. I'm calling it M. I don't know why I called it M, but okay. So now we're going to have an arrival of E. Probably should have been C for customer, but just as we've done this a number of times. So we stamp the time and we add it to our queue. So this is an arriving customer. We add it to the queue, and now instead of, now we don't have an S variable, so we can't say is S bigger than 0 because there's no S. What is the issue? The issue, we have a container M of our server entities that are available, and I just say if that's not empty, that's the criterion now. See that? Okay. And so we'll schedule our start service, and then now we need to, we'll pop off the customer in the queue, but now we'll also pop off the server from the available one. So instead of S minus 1, this has the same effect, only now we have our customer object and our server object sitting here. We can do the elapsed time from our customer. And now, okay, so here's where the efficiency comes in. These are all abbreviations. In the Java side, these will all be getters. So the customer, we would get the service time from the customer, and we would multiply it by the efficiency of our server. Yes. Okay, yeah, the question, shouldn't it be 1 minus the efficiency? It's probably just a name thing. What I'm calling efficiency is a number that multiplies the thing. So an efficiency less than 1 is faster, and efficiency more than 1 is slower. Maybe, so is there a better name for that? There probably is. Like, have you noticed that I'm sometimes challenged with naming things, but yeah, but good point. I mean, because I think things should be named in a way that are kind of more natural. And the only problem with 1 minus is that it's well, say for a slower server though, then I need to make the service time longer, and for a faster one I need to make it shorter. So I could divide by it. But that was anyway. But this is Professor Brunsman. Yeah.
It's really important. Very quickly.
Yeah. Yeah, good point. So it's right. So okay, so I'll have to work on the name. So work in progress. But now the other side of the coin on that is that it's the name of things don't matter in the model itself. That, you know, as Professor Brutzman says, they matter when it's a good name and connects with one's intuition. But the key thing is this expression right here. That's what makes it work. Just as the arrival event, by calling it arrival doesn't make anything arrive. What makes it arrive is the state transition, not the name, you know. So, okay. So now the other implication is that the end service event. Now that we have the end service event needs to have two arguments, one for the server and one for the customer. In other words, end service is the completion of service of a customer on a given server. And why do we need them both? Well, we strictly speaking, we don't need the customer except to because we want the time in the system, and that's the event where we know the time in the system. We need to know which customer has completed service in order to do that. So we could leave that off and the model would still work. It just, we couldn't, you know, we'd have to kind of do a little bit of we might have to appeal to Little's formula to get that particular one. Not a big deal. However, this one is essential because now that we've completed service, in the previous models, we just added 1 to S, but we can't do that here because there is no S. What we need to do is take that server entity and put it back in the container of available servers, and that's what we do here. And okay, so and yeah, we've done this a couple times before, so this shouldn't, you know. So there are kind of two ways of doing the arrivals. One is sort of the unlazy way of doing it by kind of redoing everything to strictly implement this. We would basically re-implement a number of things that we already did in the arrival process. This is still pretty small, so it's not a big deal. The lazy way is to subclass the arrival process. And so having done all this, we don't write any of that code. We just kind of write this extra arrival thing. So in this one, you would subclass SymEntity base and roll everything from scratch. And this one, you would subclass arrival process. And the only trick here is we would need to, the arrival event here would be calling the superclass arrival event as it goes there. But then if having set all that up, our listener diagram would just kind of look like this. You know, our customer arrival process is creating these arrivals that have our customer in them, and the arrival event with the customer in them is taken there. Now, for those doing Python, because Python doesn't support method overloading, we would have to do something a little bit different in the implementation. We'd have to say something like customer arrival. So we could do customer arrival both in the arrival process as well as here. Instead of calling this arrival, we'd say customer arrival, and then we could just listen. Or we could stick with arrival here, do customer arrival for the arrivals, and then use an adapter. So we would adapt customer arrival to arrival, and that would basically work. So let me tell you what. Let me just take just to kind of give you a peek at how this would be implemented. Oops. Now, see, I can't tell if I went. Sure, I'm doing this. All right. Just want to show you how to. Let's kind of do the server. Its superclass would be entity. You may notice that entity is a very popular name for a class, so we got to find the SimKit one. And I'm doing this for the Java one. I think I have time to do it for the Python one as well. So okay, so here's the our instance variable efficiency. And then oh yeah, now here's the like when we're actually kind of, because we're going to have two different types of entities running around the thing. Each entity has another attribute we haven't emphasized a lot called name. And when we're kind of, the default name is just entity. But here, what this is going to make the name, turn the name into server. So we can tell whether it's a server or a customer if we're doing the debugging thing in this. So now, depending on whether we want to make this a something which can possibly change, we could. All right, so let's be as flexible as possible, and let's give it a setter and a getter. Make sure this is private. That is the last method. But the thing is that this needs to be bigger than 0. Because if efficiency is 0, then that means that we can get it done instantaneously, and that's physically impossible. So if we try to do that, we're going to throw a new illegal argument exception. And we'll say efficiency. Must be bigger than 0, but you gave me this. And then, what are you? Oops. And then the other thing is that we do want to override our toString. And we don't even need anything from the other one. Let's just call it a. And then so each server has an ID, and we have our getter for the efficiency, and we're going to override that. Okay, so we can just kind of test that out by so here, I mean, here's how we would well, let's just make sure all that got in there, okay? Okay, so, and we see that it did not. See, that's why we test this out. Why didn't it get in there? It got in there because even though I wrote the setter, I didn't call it. So sometimes I do those things deliberately and sometimes I don't. So, okay, so that's why you always check. And just to, no, I don't want to leave the Python folk out here. So is this, let me. Yeah, there is, okay. So what I want is. Here I call it. Similar sorts of things. So we have our constructor, our init, our init. But and well, the superclass one, and so here except we need to do the similar sort of thing. So if the efficiency that we pass in is less than 0, then we need to raise a value error with the same thing. It must be bigger than 0, but you gave us this. But we need to have to stringify it. And we also want to do this and then a similar sort of thing. Yeah, we have this sort of little F thing that's kind of neat. So we have our self ID. D and self efficiency, which is going to be 4F. I got that right. Okay, so that's where we would do something similar. So let's test that out. As you can probably tell, my native language is more Java these days. Server. Okay, so let's print. Oops. Okay, so that worked too. Amazing. I'm surprised pleasantly because it usually doesn't work. So, okay, so, right. So, okay, so that's, and then now, of course, during the model itself is a little bit more involved. I think what I'll do on that is I'll do that offline and push it so you can kind of take a look at that, and maybe I'll go over that next time. But I do want to finish with another model, which is kind of, now this is kind of going back to our simple scaling scalar situation. But now what if you've been in supermarkets at all, you will notice that sometimes the queues kind of start to build up. And they say, we need another server at the front, and they bring one. Okay, so then what we notice then is that in our system, the number of servers that are actually available for service is not a constant as the multiple server queue is assumed so far, but is actually a variable that depends on what? It depends on what's happening with the queue. So in other words, and we look at our system, and what this particular one does is it starts the day with one checkout person, say, and then when the queue reaches a certain size, then they add another server who starts to process them. And then of course they only have a certain number of those. So now the parameter is just the total number that they could possibly do, but the number of available ones, they're the number of available, and then they're also the number who are potentially available, which is going to be, and then so how long do they stay? Well, they're going to be nice to the customers, and they're going to only like when the queue empties out and there's a service completion. In other words, if a server finishes and there's nothing more to do, then they'll leave and do something else. That's being done. Have you ever been, waiting in line and it's kind of coming up and you're getting a little antsy, and then you see a server sort of finish somebody, and then instead of taking the next person, they just leave. Isn't that annoying? So, okay, we're not going to be annoying like that. We're gonna actually wait until there's nobody in the queue before we go and take our break. So, all right, so we have the parameters or the max number of servers. We need another parameter, which is going to be the queue size to add to another server. And I don't know why I came up with capital T, but and then service times. And so we're going to assume that the arrivals are going to be coming from elsewhere. And now we have the number of available servers versus the current number of working servers. And you could argue that you could maybe reduce that a little bit, but this just kind of keeps everything, in my view, a little bit cleaner. So let's take a look at the event graph component on this. I'm going to submit my pen. Oops. All right. Okay, so right, so here's an arrival. And as you can see at the top, it's just our usual pattern. So if there's an available server, we'll start service. We should probably put highs there as well, but and then end service, we're going to have, if there's somebody in the queue, we'll kind of do that. Now, so here's the situation. What is it that would cause us to add a server? And it would only be an arrival event, because that's what would bring the queue up to that point. So, and here's where we kind of need this extra K variable, because we, let's see, if our queue is bigger than our maximum, and K is still less than this. In other words, is that the right one? In other words, we can add a server. Yeah, as long as there's how should I say? It's like if K, I think this should be. Oh, this is the wrong way. This should be bigger than T. So in other words, if we still have more to add, then we'll keep adding. But if we've run out of the potential ones, then tough. So that will schedule an add of a server. And now notice that that'll of course only happen, this will only happen if Q, if all the servers are busy. So we're going to add a server now, and we're going to add a server who's now taken from our pool, and now we can schedule, and this would be unconditional because we've already kind of the queue. This will not be scheduled unless there's somebody in the queue. So we'll schedule that, and that'll at least take them down temporarily below our threshold. And then at our end service, okay, we have if Q is bigger than 0, but if Q is equal to 0 and we have more than one working, then we'll take them away. So we've sort of added them, and then we're going to take them away here. The reason for this is we do want to always kind of keep somebody there. We could eliminate this and just so allow the servers to be 0, in which case, in this case, it would be well, we would have a problem here. So we would always need to have at least one server going. So, okay, so again, just in the simplest case, in the simplest case, we can still capture that element of things. And I'll have to double check that condition there. I don't think that's correct. So, okay. So now hopefully the latest computer assignment is now sort of a little more on track. I think you have a couple days left to do it. So that's partly why I gave you a little extra time. I wasn't sure if I got it 100% right. And I was right, but I didn't get it 100% right. So, okay.